Hello everyone, welcome to this video. In this video, we are going to solve integral of square root tan x dx. Now, whenever we have an integral where there is a square root and this is not a standard integral, first thing we would like to do is basically find some way to remove the square root. So, if it was obviously integration of root x dx, that would have been a standard integral, right? But integrals like root tan x and root cot x, those cannot be packaged like that. And as you know, in integration, we do not really have much rules for indefinite integration except for the u substitution and the integration by parts, right? Okay. So first of all, the only substitution that comes to mind to remove the square root is the most basic one. Make it a t square, right? So set tan x equals to some variable squared. So I'll choose t. Then obviously we also need to take care of this dx term. So we differentiate both sides to get sec square x dx equals to 2t dt, and therefore dx should be equal to 2t dt divided by sec square x. Also, since tan x is t square, if you square both sides, you will get tan square x equals to t to the power 4. And from the trigonometric formulas, sec square x minus 1 is simply equals to tan square x. We can substitute it for that, and therefore sec square x is simply 1 plus t to the power 4. And this term here becomes 2t dt divided by 1 plus t to the power 4. Now, with this in hand, we can write our integral I as this. Integral I then becomes root over t squared, because the tan x has been substituted as t squared, multiplied by dx, which is simply this term, right? 2t divided by 1 plus t to the power 4 dt. And if we simplify it, it simply becomes 2t squared divided by 1 plus t to the power 4 dt. Okay, so this is our resulting integral, but how is it any easier than the first one? Well, it is. If you notice this 2t square, there is something we need to do with this term in order to uh, make it solvable, like we do not really have a direct substitution here, which we can do, and then magically, the derivative of that comes in the numerator, just like a new substitution, and then we finally get a result. Nothing of that sort is going on here. But what we can do is this: we can write 2t square as t square plus 1 plus t square minus 1. And there is a reason we are doing that, which you will see pretty soon. So now, obviously, since integration is an additive operator, we can divide it over addition. So you distribute it over addition and find this two resulting integrals, right? T squared upon 1 divided by 2 to the power 4 plus 1 dt, plus integral of t square minus 1 divided by 2 to the power 4 plus 1 dt. This should also be dt. Okay. Now, here's the part. If you see an integral which is of this form, where x square plus a square divided by x to the power 4 plus a to the power 4, something like that, but of this form directly, nothing should be changed. This kind of forms are treated in a separate manner. This forms are treated by dividing up and down by t squared. So what will you get? You will get something like this: 1 plus 1 by t squared divided by t squared plus 1 upon t squared dt. And then the next term you should get 1 minus 1 by t squared divided by t squared plus 1 by t squared dt. And then we have to write, we will keep the numerator as it is, we will not touch that, but rather we will write the denominator in the formula of a minus b whole square plus 2ab, which is a square plus b square, right? So this should be t minus 1 by t whole square plus 2 dt. Again, we will keep the numerator unchanged and the denominator, but in the other way, t plus 1 by t whole square minus 2. Are you getting a sense of where this is going? Why am I doing all this stuff that might look unrelated? This is because now we are going to substitute u equals to t minus 1 by t in this first integral, and we are going to substitute v equals to t plus 1 by t in the second integral. This is because the derivative of t minus 1 by t is basically 1 plus 1 upon t squared dt. If you did it, find it, this becomes 1 plus 1 upon t squared dt, which is simply the value in the numerator of the first integral. And similarly, dv is 1 minus 1 upon t squared dt, correct? So this gives us the following. This becomes du, the numerator, and the denominator becomes u squared plus 2. Similarly, the numerator again becomes dv, and this becomes v squared minus 2. Now, there are standard integrals to find out this, and I will jot it down right here. Many of the standard books will give you this result. The first one basically is this: dx upon x square plus a square, where a is a constant, is 1 upon a tan inverse of x upon a plus c. This is the first result. And the second one, dx upon x square minus a square, where again a is a constant. This one is rather a different one. Obviously, it has nothing to do with tan inverse this time. It's natural log of x minus a upon x plus a plus c. So these are the two results that directly compare to these two integrals right here, as you can see. So in the first integral, du upon e square plus 2, our a is basically root 2. If you can notice, 2 is root 2 whole square, right? So that one becomes 1 upon root 2 tan inverse u upon root 2, and the next one is simply 1 upon 2 root 2, again a is root 2, log of v minus root 2 divided by v plus root 2 plus c. Okay, now what was u? U was, I think, t minus 1 by t, right? U was t minus 1 by t and v is t plus 1 by t. Okay, so therefore integral of root tan x dx now becomes 1 by root 2 tan inverse of t minus 1 by t by root 2 divided plus 1 by 2 root 2 logarithm of t plus 1 by t minus root 2 divided by t plus 1 by t plus root 2 plus c. And again t was root tan x, so we can simply write this as 1 by root 2 tan inverse of root tan x minus 1 upon root tan x divided by root 2 plus 1 by 2 root 2 logarithm of root tan x minus 1 by plus 1 by root tan x minus root 2 and divided by the same thing, root tan x plus 1 by root tan x plus root 2, and add a plus c, do not forget that. Okay, so this will complete our derivation of integral of root tan x. So this is the final answer, but obviously this might look complicated. No one is going to guess this answer, right? That yeah, here is this function, you can differentiate it and obviously would get root tan x. That's not obvious at all. But well, if you know the methods of how to approach this and problems of the similar kind, so you can try root cortex yourself right after doing this to see what are the differences between them and how are they connected actually. So anyway, that would complete the video. So please like and subscribe and let me know in the comments if you have any requests for any other videos. Thank you.